My talk today is about communicating with types, right? I've been a Haskell programmer now for, I don't know, 3 or 4 years professionally. Like half of the Haskell programmers in the world at the moment, I seem to be working with a blockchain company, but this isn't a blockchain talk. When I first got into Haskell, I was told 2 things which are both wrong. So I'm going to repeat them for you now. One is that the documentation is terrible. It was kind of true. It was a fair criticism, but it's getting better. The other thing people said a lot was, oh, we don't need documentation, we have types. And that's not true either. There is no substitute for good documentation. There is no substitute for prose. And yet, the idea that types are documentation is more true than I first appreciated. There's a lot more information conveyed by a type signature in a language like Haskell than I ever appreciated at the start. And it's that appreciation which is something I'd like to try and convey to you, to try and explain how rich a good type system can be these days, how much information it can convey to you, to other members of your team, and every programming project has a team. Even if you're just solo programming, there's always you and you 3 months from now when you've forgotten what you're doing, right? Every programming project is in a team, and every programming project has a history. One of the things I hope we'll see in this talk is that types can convey information not only to your team today, but to members of your team after you've left the job and someone new has come in, which should be something that makes all the managers in the room, if there are anybody, prick up their ears. And it will also give us the ability to analyze code. It's such a specific form of documentation, where it is documentation, that it allows us to analyze our code from a lot of perspectives and glean more information about our code base. And I would say that a good type system these days splits down into 3 parts. It lets you describe stuff, it lets you talk about the relationships between stuff, and it lets you describe the context in which stuff happened. So we're going to talk a lot about stuff this afternoon. And this is really the whole of computing. Stuff, relationships between stuff, and the context of stuff. That plus coffee is all of programming. So let's get started with stuff. How do we describe data in a programming language? How do we talk about the information that's going to be flowing through our system? I suggest that we don't do it this way. This is soap. Hands up who used soap. Hands up who's stuck with legacy soap. You have my sympathy. There was a look of madness in your eyes, sir. But there's a lot to be recommended for soap. It's very specific, but the big problem with it, it's not really human readable, it's not really human writable. Unless you're insane. Maybe that's how you cope with legacy soap. Also, I don't think this is a particularly good way to describe data. The big problem with Java, looking back on my years as a Java programmer, is you're not really supposed to describe data. In Java, data doesn't exist on its own. It can never be analyzed separately from the methods that work on it. Right? So you end up with this thing where you're trying to describe data, but there's a lot of noise around it before you even get started. I would like something more concise. And I think the whole world would like something more concise, because the data description that has become the de facto industry standard is JSON. Right? This is the way we describe data in the world right now. If anyone saw Sean Grove's talk yesterday, he was talking a lot about this. And the big problem with this is that we're not really describing data with JSON. We're just giving an infinite number of examples. How many JSON examples do you need from an API before you know what data it can return? And the answer is infinity. Right? You never know if there's a difference between what you assume these examples are telling you and what the actual data description is. A good language would have some way for us to concisely human-readably describe data. And ideally, machine-readably too. Because if it's just human-readable, then it's handwritten documentation that can get out of date. If it's just machine-readable, we don't seem to use it. Somewhere in the middle, there has to be an optimum solution where we can all talk about data. And it has a wonderful name of algebraic data types, which is brilliantly jargony. I'm going to give you a crash course in algebraic data types. So every language has the first part of this, products, where you mash a bunch of data types together and you get a bigger one. Right? In C, these are called structs. Java, I guess, they're pojos with the methods ripped out. But every language has some variation on let's mush some types together. Then there's sum types. Not every language has this idea. The idea that you can choose between several alternatives. So I've got clothing size here, for instance, small, medium, large, and extra large. And if your language isn't Haskell or Elm or PureScript or one of that family, and has this idea, it probably has them in enums. Right? The other classic example is hearts, spades, clubs, diamonds. That's what you'll see in every programming language book that covers enums. In a language like Haskell or Elm or PureScript, maybe a few others, I think there's some support in Swift for this, what really makes a difference is the fact that you can freely mix them, and we can start to describe very sophisticated types of data very concisely. Let's have a look at an example of one of those. Hope the font size is large enough. Yeah? So here's a description from a system I wrote a couple of years ago. I've pruned a bit out so we can talk about it. But I think this is describing what you get back when you try and place an order. It's very concise. It's handwritten, so it's human writable and human readable. It's computer writable and computer readable. And I think this conveys a heck of a lot of information in a very small amount of space about what's going on in this system. You can very clearly see that you're placing an order on a system. You might get, the purchase might be successful, in which case you get some order details back. It might fail. For some reason, the payment provider fails. Right? So like cards expired or something. Or there might have been a network failure. Right? 500. Something's gone terribly wrong. We can, from this data, we can communicate not just all those things, but convey a sense to other programmers of the priorities here, right? We sort of expect purchase successful to be the default, and then every system has or something goes wrong. But in this system, we've decided to separate out or something goes wrong into two cases. One more common, where the payment provider tells us what's gone wrong, and one less common, where the network fails. Right? And so we convey quite a lot of information about our assumptions from the domain just in a few lines. And what I find nice about this kind of system is that those assumptions are to be found in a single place. Right? Quite cheaply and very thoroughly. Right? Everything you want to see here has been described. I was imagining if you added something into this, you come into the job for the first time, you're a new hire, you're told that the payment provider has a mechanism where there's a challenge, let's say. So you try to place an order, and the payment provider says, it's not that it's failed, but you need to challenge the user to do another thing, let's say. As the new developer coming in to add this feature, you have one place to look to see if that's a response we already handle with orders. You have one place to add it. And from that point, you can grasp how the entire system thinks of order responses. Which, I know, I compare that to something like Redux, React Redux, right? Where a lot of the time you're hunting between different modules to try and get a sense of all the things that could possibly happen. The description of possible events in your system is quite widely spread out. Whereas here you can have everything quite concisely in one place, which is something I like. Let me give you another real-world example. So this comes from a system I was writing a couple of years ago. Let's just take a quick look at it. So this is the front end of an event-based system. This was a PureScript system, but we did a prototype in Elm. They were very similar from this point of view. And what kind of events are we allowed in this system? Well, heat map items get loaded. The camera moves. You can toggle whether you're showing heat maps. And there are some payment things. There we go. We've got what's that? 8 effective lines of code. And I think this conveys to anyone reading it quite a lot about what this system did. Right? There's a lot of map information, there's payments. It won't surprise anyone to read this and learn that the whole business model was selling heat map-based data on a map, right? There's 8 lines of code, and we know something about how the architecture works. We know something about what can go right and wrong. We know something about the business model. That's a very, very concise description that conveys a lot of information. And to a certain degree, it's information that you could discuss with someone who is a business analyst, right? I think you could sit anyone down with this and have a reasonable discussion about what's going on in the system. So that's data description. Let's have a look at relationships between data. Every programming language has some way of describing relationships between data, but you may not think of it that way. This is JavaScript. A withdrawal is something that takes a user ID and an amount. Is that a relationship? Well, let's have a look at another language which puts some types in it. Java. A withdrawal is something that has a string user ID and an integer amount. And the main thing it's adding here is you get some sense of what it's returning. Right? It's returning a string. I'm sort of assuming that JavaScript and Java are the universal lingua francas of programming. But, you know, if you have trouble reading this, put your hand up, please. If you have any questions during the talk, put your hand up. I like questions. If we take that into the space of Haskell, it's a different notation, but it's saying the same basic thing. A withdrawal is something that takes a string and an integer and will give you a string back. Right? Or you can see it as a relationship. Withdrawal needs some things, and it provides a thing. The thing it provides is always at the end. Everything else is things it needs. And this is describing a kind of relationship between what you have to supply as a programmer and what you can get back if you do. The main difference here is that in Haskell and Haskell-like languages, that description of the relationship stands alone. It's not mixed up with variable names or implementation details or other syntax. You get to see the relationship very concisely on one line. There is something very wrong here. I hope a couple of you at least are twitching at this type signature, but we'll discuss that as we go along. But for now, let's look at some more concrete examples, because this is getting quite abstract. So let's have some concrete examples in Elm. Why Elm? Because it has really nice error messages. I'd like to show you some nice errors. It's also great, you know. So this is something I was doing in a project, I don't know, again a couple of years ago in an Elm project. Simple requirement, but it would let us see how these things work out in practice. I needed to generate this HTML, right? If you've used glyph icons, 3 spans with the right CSS classes, and you get this helpful message, which will come in handy in about an hour and a half, I think. So the first implementation of this, I can't remember whether I'm guilty and I wrote it and someone code reviewed it, or the other way around. Let's pretend for the purposes of the stage that I code reviewed the bad one and got the right answer. This is the first implementation of it. Icon, and you give it a name, and it builds the CSS class for you. Simple example, but it illustrates all the points I want to go into. So, what's the type of that? It's string to string. which is very vague, very vague. In fact, I would argue that string to string is the world's vaguest type signature. It's a terrible type signature. It's a red flag if you ever see it. What is foo here? Foo takes a string and returns a string. Is it icon? Yes, we've just seen it is. Is it to upper or to lower? Yep, it's that as well. Reverse, abbreviate, humanize, all of the above. It's a really vague type signature. Any Haskell programmers in the audience will know there are more general type signatures, but I don't think there's anything more vague than this. It's also Turing machine. This is the type of Turing machine, right? You can encode one of Turing's tapes as a string and have the output as a string. This is the universal type signature, and it's terrible. If you ever see it, change it. So when I saw string to string, I thought something's going to go wrong here, and I can tell you two things instantly that will go wrong with this function, just from looking at its relationships. The first is that someone calls icon with a typo, right? This displays nothing. This will come back from QA with a bug report saying, I know someone loves to drink, but I don't know who. It's me. The other thing that goes wrong here, so wrong input, no clue as to what we're supposed to give to it. The other thing that can go wrong here, and this is pretty horrible, is you can accidentally end up calling the same function on the data twice. I've actually seen this in real code where someone defines the result first and then accidentally calls the function on it again, and you end up with this nonsense where the thing has just run over the string twice. Terrible type signature. But it also gives us an idea of how we fix that type signature. We do something like this. We get more specific. We use the type system to describe the relationship more effectively. Right? We say, okay, what this is really doing is taking some kind of idea of icons and turning it into HTML. That's what we're supposed to do. Here's the implementation. Slightly different syntax because we switched to Elm, but basically the same thing, right? And now this is fixed. This won't be used incorrectly. If you want to know what icons are available to you, you just look at the thing at the top. If you want to add another one, you just go for it. System works a lot better. Small example, but it scales up. So this is an example where the type signature reveals quite a lot of information, both to the computer and to you, the programmer. It reveals the structure of our code and tells us that it's floppy, flabby, not specific enough, which raises problems and gives us an idea of how we might structure a solution to fix those bugs. Let me give you another real-world example. So this is quite similar, but it leads somewhere else. This is a routing function in an Elm web app. So you get the fragment of the URL, and you're trying to figure out which page you're going to display. Right? Standard stuff. So it's just, this is a pattern match, and if all else fails, it 404 page. If you look at the type signature of this, again, it's that horrible vague type signature string to string. It really should be something like this. We become more specific about the view. We can't really become more specific about the input. I mean, a URI, you can tie it down a bit, but basically that thing is always going to be a user-entered string you can't rely on. But you can rely on the output. And this leads to some nice properties. Because now we've specified which pages are real, we can talk to the third person that's always on our team. Right? There are always two people in your team, you and future you. If you do it right, there's a third person on your team, which is the machine. You know, compilers don't always have to be adversaries. They can be working with us if we give them the kind of information they can read. So we write up this, fix the whole thing, and here we come along to actually use that view type. Here's where we're going to render out the different types of view, and we've forgotten something. What have we forgotten? The fact that we've said that one of the views is not found, but we've not written any code to handle it. The compiler has caught an error for us, because we can have this conversation not only with other programmers, but with the computer. I mean, and the great thing about this is that whilst machines are dumb, they're very thorough. They don't miss edge cases. This is something that if you forgot it in a JavaScript app, it can very easily get to QA or to your users before you realized you've missed out coding up the 404 page. So it keeps you honest. I like this. One more example. So this is one where, actually, let me show you and tell me what you think, right? So here are two functions I'm going to show you. The first is just a simple, structurally it's very simple. It takes a Boolean and returns a string, right? So you're either happy or you're sad. Versus this version, which takes a mood and returns a string, right? Are these two equivalent? That's the question. You get hipster points if you say that mood and ball are isomorphic. Are they equivalent? Well, structurally they seem it, but there's a very important difference between these two things, which is that the first one allows you to say show mood 2 is greater than 50. Right? This is an example where you're allowed, as a user of a relationship, a user of a type signature, you're allowed to talk nonsense, which is not good. Whereas the second version rejects this meaningless statement. Even though the first one is type correct, it's meaningless. Whereas the second one, because we've narrowed the scope of things and communicated what our intentions are for how this will be used, we've got a much richer feedback system going on. And you get this lovely message, which gives you a clue about what you're doing wrong. And you get it fast. I like fast feedback. Whenever you have a type error, you always get a type error. The question is whether you get it from QA or from your users or from your bug reporting system, or do you get it now, like 30 milliseconds later? I like fast feedback, except from my wife. So let's go back to withdrawals. If you're watching, honey, I didn't say that. She never watches my talks. My father-in-law does, and he doesn't understand any of them, but it's very nice. So let's revisit withdrawals. Go back to this example, because we're going to spend a little more time with this. So we've got this function. Can we enrich it further? Did anyone twitch earlier when I showed this type signature? Yeah, good, well done. The trouble with this, if you want like a direct comparison, is it's got exactly the same type signature as repeat this string n times. So we know that structurally it has the same high-level abstract analysis as something completely unrelated. We should really be enriching this to something like takes a user ID and an amount and returns a withdrawal ID, right? This is a much richer thing to communicate to the computer, but also to communicate to our colleagues. No one's going to say, what's this first string and what's this last string now? Right? It's very clear how you're going to use this in practice. You sent a lot of information to your colleagues whenever they happen to read it. This is a great improvement. We can go a bit further. And up to now, pretty much everything in here, you could say, I could do this in Java, Flow, TypeScript. You might be interested in those. There are a lot of languages which have something like this. Maybe not as concise, maybe not as neat, maybe slightly more as an afterthought than as a core idea. But up to this point, pretty much, there are a lot of languages that handle these ideas. And if you can't go back to work next week and use Haskell, then maybe you can incorporate some of these ideas into language extensions like TypeScript Flow. But this is where Haskell gives you an extra level on things, which I really like, which is context. Right? Types are not just about stuff interacting with stuff. It all happens in a context. And being able to manage context is one of the best software complexity tools I know of. It's an idea I've only encountered in the past, like I say, 3 or 4 years. But it's fantastic, and we should be using it more, and it should permeate the programming landscape. But it's usually totally overlooked, which is a shame. So let's have a look at some functions and ask ourselves, what context are these functions happening in? Show greeting, right? Show greeting takes a user and returns a string. You could imagine this is going to say something like, it's going to look at the name and the title and say, "Dear Mrs. May, thank you, but your services are no longer required." You know. Or fetch user, that's going to take a user ID and return a user. Presumably, this is going to make an AJAX request, something like that. It's going to fetch something from a store in order to turn a user ID into a user. And the last one, create an invoice. It's going to take an order ID and a user ID and create a PDF of your customer's invoice. Feels like, again, communicate a lot of information from that type signature. I don't think you can do it. I don't think you can take an order ID and a user ID and create an invoice. This suggests to me somewhere it's going to go to a database, right? And look up those two keys and create the thing. In Haskell-like language, there is a way, and I'm not going to delve too much into the details, but there is a way to augment the return value with the context in which that return value is calculated. So you can say something like this: withdraw is a function that needs a user ID and needs an amount and will provide you with a withdrawal ID if you run it in an SQL-ish context. Right? Hipster points for saying higher kinded types. I pretty much add that so that you can go and Google it. We're going to look at the effect of it rather than the mechanics of it. So we can start to augment our return values with where you have to be in the larger context of the system in order to get that return value. The first one, show greeting, doesn't really need a context. It's just a calculation, right? So this is a pure function. The second one, yep, it needs AJAX requests. So I can instantly tell from that that it is susceptible to network errors, right? Show greeting isn't going to have any problems with network errors, whereas fetch user, yeah, it needs the network to be up. It's going to have the usual suite of 404, 500 errors that you might expect. Create invoice, it's going to go to the database. I instantly know some things about this. It's going to be a pain to test. It's going to be slow to test because I've got to spin up a mock database. Or it won't be tested because a lot of the time, anything that requires testing against the database gets skipped. Or, gets tested against a completely different database. So you've got your production database, which is Postgres, and your testing database, which is SQLite, because it's a lot easier. But the discrepancies bite you. I know that this third function is going to be the hardest to test, and I know that the first one is going to be relatively easy to test. Because I've got a way of documenting what context it happens in, and because I've got the computer checking it. And this is a very important point. I didn't want to get into correctness. The argument, my code, the classic static dynamic argument. You allow programs that aren't correct. Well, you disallow some programs that are correct. But the property that having a compiler gives you is when you look at this as documentation, you can rely on it. You know if it's accurate instantly, or near instantly. So this kind of mechanism, it reveals dependencies that your code assumes about the world around it. And it also reveals the lack of dependencies, right? That first function we know is pure because it doesn't require any context. The compiler checks if it's true, so we can rely on it, unlike every other kind of documentation in the world. I've lost count of the number of JavaScript projects that have fantastic documentation that was correct in the last version. This is very sad. There's a lot I love about JavaScript, but I do not like debugging the latest version of the config file, which was slightly different from the last one, with no clues about what's changed. As well as revealing that, it also, again, reveals some design decisions we can make, which are quite nice. So let's have a look at that. Creating an invoice. This takes an order ID and a user ID and will go off to the database and eventually give me back a PDF. I see a couple of problems with this one. The first is that I don't think this actually needs to be able to write to a database. So I'm going to constrain its context to SQL read, which is something I've made up for my system, but I'm quite able to do that. I have the tools available to make a read-only context for queries. And now I've eliminated a lot of problems, right? I've eliminated any bug I have that's writing weird stuff to the database. I know it's not coming from here. I might split this into SQL read and SQL write. And then if I have a problem where the database is being written too weirdly, I only look at the functions that involve SQL write. I don't need to bother with this one. I don't need to bother with any function that doesn't say SQL. I really constrain down the footprint of what this thing can break, which is nice. Also, as a more positive benefit, if I do this and my site starts to get busy, I know all the queries that I can instantly offload to a read-only database. Right? I just have to grep for SQL read, and I can shunt all those queries to a read-only secondary database and know that they're going to work because I've already been having the compiler check that this only needs read permission for the past N months. To give you a real-world example of this, I was writing some stuff against Firebase last year. Have you ever used Firebase? It's like a cloud-based database that's quite nice. It does WebSocket-y stuff, so you get instant streaming updates. For some projects, it's fantastic. And I was writing some code that talked to Firebase, and it took a while to get it right. So I put Firebase into the context of all my Firebase calls, and when something went wrong with the data, I knew exactly which parts of the system could have been broken because they're talking to Firebase. And I knew all the parts to ignore. Right? It really narrows down your search space when things break, because you've narrowed down the context and had it permanently checked. And another thing this suggests, so make that change, and now we're in a SQL read context, and I look at this and I say, actually there's still another thing that's very wrong with this. We could greatly improve this by splitting it out into two things. Because by looking at this SQL read PDF, I think, hang on, what is it about going to a database that generates PDFs? Nothing. These should be teased apart to the thing that fetches the data we need and the thing that converts it into a PDF. Right? This is a huge improvement, because if you're going to test these two, I think generating a PDF is the thing that's more fragile, more prone to change, more prone to business demands affecting it, and it's now a pure function. So it's really amenable to testing. Whereas the one that's a pain to test, the database query, is actually going to be pretty straightforward, right? It's two primary key gets. I might not even bother testing that. I might. But the stuff that's hard and fragile has now been stripped into a pure function. This is standard decoupling, right? And I've used a lot of languages where they talk almost religiously about the value of decoupling. What I like about Haskell is I can look at this type signature and get clues about where decoupling should be happening, because it gives you an abstract analysis of what's needed, what's provided, and the world it's happening in. I can get a sense of what's taking on too much responsibility. All this really limits the scope of what a thing can do. So this is the big thing, right? A good type signature conveys a heck of a lot of information to you, right? It describes what's possible. It describes what data can flow where. Equally importantly, it excludes possibilities. We cannot provide this function with a Turing tape anymore, right? A good type signature clarifies the relationships between bits of code, makes them less vague. And it reveals them for analysis. I really like languages where the type signature stands alone from the rest of the code, because I can just stop and analyze code in the abstract with no other noise. And it highlights the scope of your function and constrains the scope. So your more complex functions have a much smaller footprint. These are great things, and I advise you strongly to look for a language that provides them. So let's have some propaganda. Where would you use these? So this is Elm, PureScript, and Haskell. If these ideas are completely new to you, I would recommend Elm. It's a great language. You can build some great stuff with it. It's very friendly. Of all these, the compiler is trying to be on your team languages. Elm wins on that metric. If I were teaching someone programming today, Elm is the language I would choose. PureScript is a very hot contender. These two are both languages that compile to JavaScript, so they're very front-endy. You can use PureScript on the back end as well if you wish. Is that still true of Elm? Not really. Ish. No. So these are front-endy leaning languages. You would choose PureScript if you are already familiar with some of these ideas and you want to dive into some of the meatier, more academic stuff that Elm programmers will tell you you don't need. And Haskell is probably the most famous of the three. If you really want to dive into the world of exploring types and type signatures and all the things you can express, because for the last time, it's not about correctness, it's about being able to express ideas and read them. Haskell is kind of the flagship for that. But also, if you don't have the chance to use those, a lot of these ideas will hopefully help you use things like TypeScript and Flow. They might help you choose between the two of them a bit more effectively. They might help you choose between Rust and Go, which also get compared. Rust is really interesting to me in that it doesn't quite have the same type signature, type ecosystem thing. One thing that's interesting about Rust, though, that Haskell doesn't do, is it kind of has compiler assistance for managing the context of memory. I think it'd be really interesting if we had languages where you could model context of memory use and context of CPU use, context of network usage. These would be interesting things. Rust is probably the closest we've got to a production version of that. If you want a couple of book recommendations, oh, I forgot one. If you want a couple of book recommendations, Elm in Action by Richard Feldman is currently in MEEP. And he will tell you about it if you want to hear it. Type-driven development with Idris is a great one which takes these ideas even further into the land of dependent types, where you can describe a lot more relationships. And I've just started this one, so it's not so much a recommendation as a, oh, let's have a look at this. Thinking in types is, again, taking these ideas further. Yeah, but that's what I have to tell you. Types, communication, design, ideas, go learn them. Thank you.